Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. It's March 26, 2023. The time is around 12:15 a.m. Okay. My topic for this morning, it's already this morning. It's past 12. Okay. My topic will still be a long-form video on advanced mathematics. Okay, I will check my camera. Oh, it's still fine. It will be advanced math lesson number 24. Okay. This is now the so-called alternate Laplace transform solution of RC-DC circuit. This is similar to the last topic, advanced math lesson 23, but this will be an alternate solution. I want to show you an alternate solution on advanced math 23. So I mark this as 24. It's the same problem, but I will be presenting another alternate solution so you can see the variance or the difference of the two solutions. Okay, let's proceed. The given circuit is still an RC, series RC, energized by a direct current source. And the problem is asking what will be current as a function of time by using Laplace transform. Okay, let's proceed. So you could see the difference of the solution for this morning and the solution from the previous one. For the solution, if you take the summation of voltages equal to 0, upon closing the switch, there will be circulating current. And if we try to take the summation of the voltages, plus E minus B sub R minus B sub C, and this should be equal to 0. Plus E, this should be equal to, we place this 2 here on the right, so it will now be IR plus 1 over C, the integral of I dt. So actually, after taking the summation of the voltages, what comes out is not actually a differential equation. It was an integral equation. Why integral? Because we got the integral sign over here. Right? So for the meantime, after taking the summation of the voltages, what comes out is actually an integral equation. And for tonight, instead of solving this one directly, because the previous, the previous solution was, we solved this one immediately as an integral equation. And for tonight, we will change this integral equation to a differential equation. Okay, so after changing that to a so-called differential equation, the solution will be different from the previous one now. Okay, so taking the differential of both sides, the differential of E is 0. The differential of Ri will be R. Current is variable, it will be di. Plus 1 over C. I'm following this. The integral of the differential of I dt, okay, it will be something like this. Hold on. The differential of the integral of I dt, okay, will just be simply I dt. Because when the differential sign goes near this integral sign, they will try to cancel out each other. So they will try to cancel out each other, or this will be gone. So the integral of the differential of I dt will just be simply I dt. The integral, the differential of the integral of I dt will just be simply I dt. So for the second part on the right, it will be just be simply 1 over C times I dt. And multiplying all terms by C, 0 times C will be 0, RDI times C will be RCDI, and 1 over C I dt times C, this C here cancel with this, right? So what remains on this part here will just be simply I dt. And if we try to rearrange this one, RC di dt plus I should be equal to 0. That is by multiplying all the terms by 1 over dt. Okay? This equation here multiplied by 1 over dt, 0 times 1 over dt will be 0. Okay? RCDI times 1 over dt will be RCDI dt. I dt times 1 over dt, this dt here cancel with this. So what remains will just be simply I, and this should be equal to 0. You got it? Oh, I will erase this one so it will look nice. So what comes out after the manipulation is now a first order DE, meaning differential equation. You see the difference now? After taking the differential of all the terms, what comes out will now be a first order differential equation. So we eliminated the integral equation. So after bringing out the equation to be under first order differential equation, we could now proceed with the solution. And that solution is the one I'm saying, the so-called alternate solution. Okay? Taking the Laplace of both sides. It should be RC, the Laplace transform. Di dt is actually the derivative with respect to time of I. This is Laplace, right? Plus the Laplace transform of I, and this should be equal to 0. This is RC, and the Laplace transform of any differential thing is actually S function capital, what is this? Capital letter S minus, what do you call this? Small letter f as a function of f sub 0 plus. Okay? That is the Laplace transform of any differential thing. It will be S, capital letter F as a function of S and f sub 0 plus. And for the meantime, the variable is actually current, so this should now be current. So this is actually I sub 0 plus. Okay? So we will follow this. So this will be RC. The Laplace transform of any differential thing is actually S, capital letter F as a function of S, but capital letter F is actually current, so it should be capital letter I as a function of S, minus the small f will be the small letter equivalent of this, it should be I sub 0 plus, close bracket, plus the Laplace transform of I will just be simply capital letter I as a function of S, and this should be equal to 0. That's why our topic for tonight is actually the so-called solution by using Laplace transform. And for the meantime, it is the Laplace transform of any differential thing. Okay? By following this. Okay, simplifying. We multiply the first one here. So this will be RC times S. This is RCS. Capital letter I as a function of S. We multiply this one here by this RC here, so it will be RC I sub 0 plus I as a function of S, and this should be equal to 0. This is actually the initial condition for the problem. And using the equation to solve for this one in terms of capital letter I as a function of S, okay? Using the equation originally, E is equal to IR plus 1 over C, the integral of I dt. E is equal to IR. The integral of I dt is actually Q, the charge on the capacitor, all over C. At time t equal to 0, we assume that the initial charge on the capacitor is 0. So we put this condition here back here. E now should be equal to small letter I, I'm following this, times R, plus 0 over C. 0 over C is actually 0, or this will be gone, right? So I sub 0 plus, I will place the quantity now, I sub 0 plus this one here, should be equal to the ratio. We multiply the terms by 1 over R, right? So E times 1 over R is E over R. And this I will mark that now as I sub 0 plus, meaning the value of the function at time t equal to 0. So at time t equal to 0, the value I sub 0 plus is actually e over r. That refers to the so-called constant of integration actually, if we are referring to integral calculus. Okay, so taking this value, we place it here. So what comes out? I will check my camera. Still okay. I will continue with this one. So RCS, capital letter I as a function of S, minus RC, I'm following this. I sub 0 plus from our computation is actually E over R plus I sub S. I, capital letter I as a function of S, and this should be equal to 0. And if we try to factor out, there's a common factor, capital letter I as a function of S. So this is capital letter I as a function of S times open bracket RCS, the coefficient, right? RCS. This is plus 1, close bracket, equal to. Luckily, these are here, cancel with this. So what remains on this one will be CE, and we place it on the right hand side. So this will be, the right hand side will be CE. And if we try to multiply this equation here, we want to eliminate this one. So we will just take the reciprocal of 1 over RCS plus 1. Okay. So the left hand side multiplied by this will cancel out. It will just be simply capital letter I as a function of S equal to the right hand side, it will be CE all over this. CE over RCS plus 1. Okay? By using algebraic manipulation, this is now the one we are telling that by using Laplace transform, we could bring out the solution by only using algebraic manipulation. Okay, let's try to manipulate. We will divide the numerator and denominator by RC. So this will be CE over RC. This is RCS plus 1 over RC. Okay? What you do on the numerator, do it on the denominator, so there will be no violation. Okay? So what will come out? I will just rewrite this one, CE over RC. Okay? The simplification of this, RCS divided by RC is actually S rather. And 1 divided by RC is actually plus 1 over RC. You see it? So if we change the operation, so this is now actually gone, right? After the division. So to change the operation from division to multiplication, we will take the reciprocal of this. Okay? And the equivalent of this is actually 1 over S plus 1 over RC. So it will be 1 over S plus 1 over RC, close quantity. And luckily, this C here, cancel with this. This C here is gone. So what remains on the right will be the coefficient. It will be E over R times the quantity, 1 over S plus 1 over RC, close quantity. And I think this is now the final capital letter I as a function of S, okay, we are looking for. So to bring out current as a function of time, we will take the inverse Laplace of both the left and right. The inverse Laplace of I capital letter S is actually I for the left hand side, the one we are finding. And for the right hand side, E over R is constant, right? So we don't touch as 1. We will just take the inverse Laplace of 1 over S plus 1 over RC. And this is actually similar to 1 over S plus A. And this the inverse equivalent of this is actually E raised to minus 80. Okay? From the table that I've given you, the one we have derived, so the inverse Laplace transform of 1 over S plus 1 over RC will follow this. It will be E raised to negative T over RC. Because the value A is actually 1 over RC. So if this is plus, this will now be minus. So it will be minus 1 over RC times time. or it will be negative t over RC. So the exponent of A is actually e raised to negative t over RC for this. Therefore, the final solution now, current as a function of time, small I, the one we are looking for, this should now be equal to, I'll just follow this, it will be e over r. The inverse Laplace of this, it will be e raised to minus t over RC. That's it. Same as the previous lesson number 23. The current as a function of time for an RC-DC circuit is actually e over r, e raised to minus t over RC. That is, if we try to graph this one, the abscissa is time, the ordinate is actually current, okay? It will be something like this. At time t equals 0, this is the value. Then as time passes by, going to positive infinity, the current is almost 0. So this graph here refers to this. Oh, that's it, guys. That's the alternate solution by using a first order differential equation instead of the original integral equation. Because actually we could change the form of this to a differential equation by just taking the differential of both sides. Because integral and differential try to contradict each other. So if we try to take the differential of the integral of I dt, it will just now be simply I dt. So after taking the differential, what comes out is actually a first order differential equation. And after coming out, the first order differential equation comes out, okay, we could use the Laplace transform of any differential thing. That is S, capital letter F as a function of S, minus I sub 0, minus small letter f sub 0 plus. This f here, for the meantime, is I. And this small letter f is actually small I. But to continue with the solution, we must have to compute for the value of this by using the condition at time t equal to 0, Q sub 0 on the capacitor. The charge on the capacitor at time t equal to 0, the capacitor is not charged. So the charge on the capacitor is 0. So if we try to substitute, this will be 0. And 0 over c will be 0. So what comes out is simply I sub 0 plus will just be simply e over r. And that is actually the so-called constant of integration under definite integral. Oh, that's it, guys. So for those of you who are taking advanced mathematics, this is for you guys. If you want to subscribe to my channel is at youtube.com/@proofdvj. And if you want to share it, please click share. Good morning from Los Angeles.